Section 8.5, we're going to get some more accurate higher order methods for solving our first order equation y prime equals f of x and y. Euler's method is based on using the first two terms of the Taylor series, that is y of x plus h is y of x plus hy prime plus h squared over 2y double prime, etc. You throw away this term here and replace y prime by f of x and y, which is the differential equation, and that's Euler's method. And the Euler's method ignores this term, that's order h squared, so it has local error of order h squared, but that means overall global error order h because there's a total of n steps where n is proportional to 1 over h. So the obvious way to get a higher order method would be to include more terms of the Taylor series and approximate y of x plus 8. See that all of our methods, the basic goal is to get from the solution at x to the solution at x plus h, or x sub n plus 1, which is x sub n plus h. So how do you get from the solution at xn to the next point? Well, Euler's method just uses the first two terms of the Taylor series and replaces y prime by f. You could take three terms of the Taylor series, in which case your local error would be order h cubed and your global error would be order h squared. But the problem is, what's y double prime? Y prime is given by the differential equations. That's y prime is f of x and y. But what's y double prime? Well, you have to get y double prime, you have to differentiate the differential equation. For example, if the differential equation is y prime equals minus y plus 2 cosine of x, you just take the derivative of both sides with respect to x, not with respect to y, derivative with respect to x, and that is what then y double prime is minus y prime minus 2 sine x, and you can use that for y double prime. Now if you want to go one more term, as we're going to do for our problem, we're going to go out to the h cubed over 6y triple prime term and then ignore the fourth order term. So our method, we'll call it a Taylor third order method because it's fourth order local error, which means third order global error. So we're going to need two more terms. We'll get y double prime by differentiating the differential equation once, and y triple prime by differentiating it again. Well, here's our Euler's method program for y prime equals x cubed over y, and the exact solution is that. And Euler's method just uses two terms in the Taylor series, and x goes up by h every time y goes up by h times y prime, but we want to go up another h squared over 2y double prime plus h cubed over 6y triple prime. But what are y double prime and what are y triple prime? We have to differentiate this with respect to x. So here's our Taylor 3 program. It's exactly like the Euler program, except now we have not just y goes up by h times y prime, but plus h squared y double prime over 2 plus h cubed y triple prime over 6. But the hard thing is, what are y double prime and what are y triple prime? We know what y prime is, that's the differential equation. To get y double prime, we have to differentiate that with respect to x, remember. And what's the derivative of y with respect to x? It's just y prime. So we take the derivative of that, we use the quotient rule, square the denominator. In the numerator you have denominator y times the derivative of 3x squared minus x cubed times derivative of y, which is just yp. So that's y double prime in terms of x, y, and y prime, which we just calculated, so I don't need to expressly put in what y prime is. It's calculated there. Notice I have this commented out. I simplify a little bit because I have to take another derivative. I want a third order Taylor series method, so I factor out x squared here and just commented that out, and it's easier to take the derivative, although it's still pretty hard. So now we have to take one more derivative of this with respect to x, and this is kind of a mess, but it's x squared times something. So I first take the derivative of x squared, which is 2x, then times the something, plus x squared times the derivative of this from here on, and that I have to use the quotient rule. I squared the denominator, which is now y to the fourth, and I have denominator y squared times the derivative of numerator, which is 3y prime minus, I have to use the product rule here, minus derivative of x, which is 1y prime, minus x times derivative of y prime, which is y double prime, ypp. But see, we've already calculated ypp, so that's okay. Minus the numerator times the derivative of the denominator, y squared. The derivative of y squared is what? 2y y prime. So there's y triple prime, and we're in business. And let's try it. Okay, now the error is much smaller than with Euler's method. It's like 10 to the minus 6. And you can see that the error is going down by a factor of 8 each time. When I cut h by a factor of 2, error goes down by a factor of 8, another factor of 8, which is what you'd expect for a third order method. Remember, Taylor series ignores the order h to the fourth term, so its error per strip is proportional to h to the fourth, but the overall error, since the number of steps is proportional to 1 over h, is h cubed, so that's when you cut h by a factor of 2, you expect the error to go down by a factor of 8. Well, the Taylor series methods are nice and stable and accurate. Only one problem, and it's pretty obvious what it is. It's a pain in the neck to calculate these derivatives. This one is particularly bad. If I wanted to add another term, I'd need to take a derivative of that, and it gets worse and worse, although some problems it doesn't get worse and worse. But Taylor series methods, even though they're nice and stable and accurate and work perfectly well, it's a pain in the neck for the user to calculate those derivatives. So in this section we look at another method, a series of methods, family of methods, the Runge-Kutta methods, which don't require the user to supply anything except the function, the right-hand side of the differential equation itself. And they're also very accurate. So there's a whole family of methods. This fourth order Runge-Kutta method is one of the most popular. It's very easy to program. It's hard to analyze. You know, how do you derive it? Well, somebody derived it, Runge and Kutta apparently, and we can just use it and without analyzing it. But basically it's really easy to program. You just put all this inside a loop, and every step x goes up by h, and y goes up by h times 1/6 of this, where each of these is f at some point. And the only insight I can give as to why this works so well, notice they say the truncation error, the local error is order h to the fifth, which means we expect the global error to be order h to the fourth, and it will be. But where in the world did this come from? Well, if f happens to be a function of x only, then this is just Simpson's rule applied to integrate both sides of the differential equation. You integrate y prime and you get y at x plus h minus y of x. Integrate the right-hand side using Simpson's rule, and you get exactly this. Notice these weights look familiar here, 1/6, 2/6, 2/6, 1/6 of the derivative of the function at the left point, right point, and 1/3 and 2/3. So it's basically reduces to Simpson's rule when f is a function of x only. When it's not so obvious, but it's not surprising that it's order h to the fourth, because Simpson's rule is global order h to the fourth. But it's easy to program. And here is our Runge-Kutta fourth order method applied to the function x cubed over y. So I defined the function up here because I got to call it a bunch of times. So it's whatever your right hand side is in terms of x and y, you can put that there, and that's the only change you need to make if you want to solve another problem. And again, I'm using 3 different values of h, cut h by a factor of 2 every time, and basically this is just the formulas in the book, just with a loop around it to do in steps. And I calculate the error again and the ratios, and this time if it's fourth order it should be a ratio of about 16. and indeed it is. The error is even smaller than the third order Taylor series method. This is 10 to the minus 7th times that, so this is like 2 times 10 to the minus 9th. Very high accuracy. Every time I cut h by a factor of 2, the error goes down by a factor of about 16, which is what we would expect. Whatever method you use, Runge-Kutta, Taylor series method, Euler's method, which is Euler's was just Taylor 1. For real world problems, you often need to make the routine adaptive. That is, there's no reason why h has to be constant. Each h is independent of the other, so you could take small steps for a while and then larger steps. And for some problems, that's very important to do. In fact, it's more important than what method you use. And so there are sophisticated routines will choose the step size adaptively. How do they do that? Well, they take a step with one method and then go back and take it again with a different method and compare, like getting two opinions from two different doctors. Two different methods, compare them. If they agree very well, then they're happy and they go on. If they don't, they say, well, h must be too large, so we'll go back, not all the way to the beginning, but to the last step and cut h by a factor of 2, say. And that's what this method does here. It actually uses 2 different Runge-Kutta methods, so every step it uses a 4th order Runge-Kutta method and a 5th order method and compares them. And if the error is too large, it goes back to the previous step, not all the way to the beginning, and cuts the step size. If it's too small, that is, if it's a lot smaller than we need, than the error tolerance required, we'll increase the step size. So here's an example of this with this method applied to this differential equation, which has a solution that looks like this. So it clearly needs to take there's no need to take a small step here, but here things are changing real fast and you need to take a smaller step, and then you can increase it again, and that's what the adaptive method does. It increases the step size. When it gets close to this, it says, whoops, I'm not getting very good results. I need to take a smaller step size until it's happy, and then it gets out here and says, okay, now I don't need to take such a small step size because my error is small. So that's roughly how adaptive methods work. Sophisticated routines like ODE 45 and MATLAB will automatically vary the step size as required, and the user just says how much error he wants and they'll adjust the step size appropriately. And we're skipping section 6 on multi-step methods, but let me just say a little bit about it. Overview. Here's a typical multi-step method. That is that the new y, the y at the new point, depends not only on the previous y, but several before that. The Runge-Kutta and Taylor series and Euler's methods are all one step. You don't need to go back to the yn minus 1 to figure out yn plus 1, just need yn. So there's some obvious problems with the multi-step methods. One is they're not self-starting. You've got to use some other method to take the first few steps. Before you can calculate yn plus 1, you need to know yn minus 1, yn minus 2, so you got to take a couple of steps using some other method like a Runge-Kutta method. Another problem is that some of them are implicit. That is, this involves x of n plus 1, and you don't even know y of xn plus 1 yet. So that's a problem. And another problem is it's harder to vary the step size. For an adaptive method, you want to change h, but they're derived assuming h is constant. So several problems. The disadvantages. So why even bother with multi-step methods? Well, the main reason is they're useful. In particular, the implicit ones are useful for certain type of problems called stiff problems that other methods like Runge-Kutta don't do well on at all. But we're skipping them.